Welcome to the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. So let's get moving with this next one. Bam! So today we are talking about Gibbs Free Energy. And that's labeled as delta G. Okay, delta G naught is equal to delta H naught minus T delta S naught. Okay, so what is delta G naught equal? That is the Gibbs free energy. That is the energy to do useful work. Remember that? Useful work. Okay, the delta H naught, that is the enthalpy term, and that is a heat term. Okay, we talked about the internal heat and the pressure volume issues with the enthalpy already before with a previous video. And the delta S is the entropy term, and that is a disorder term, if you will. Okay, so let's get into the details about this and the signs of these numbers or these parts of these to figure out what is going to happen with the Gibbs free energy value. So when it's a spontaneous reaction, that would be product favored. Okay, we're going to have the delta G naught as a negative value. Now I know delta G naught will always be negative if the enthalpy term, that's delta H, is negative. That is exothermic, and the delta S is positive, and that's disordered. So the delta S term itself is positive, but there's that negative sign in front of the T delta S that makes that whole term negative. So if the delta S is positive, the delta H is negative, then I know that the delta G is negative, and it will be spontaneous and product favored. Okay? Now, for a non-spontaneous reaction that is reactant favored, the delta G will always be positive. When the delta H, that is the enthalpy term, is positive and endothermic, and in addition to that, the delta S is negative, and that means more ordered to the system. That means that when delta S is negative, then the whole term T delta S with the negative sign in front of it would be positive. And the enthalpy, or the delta H term, is positive. That means that whatever numbers you put in there for the enthalpy and the entropy, the delta G will be positive, and it will be non-spontaneous and reactant favored. Okay? Now, the question lies when the enthalpy, that's the delta H, is positive and the entropy term is positive. So when they are both positive, then, well, I don't know what the sign of the delta G will be. I actually have to plug in the values here because it depends on the magnitude of the delta H, the enthalpy, and the delta S, the entropy term, to figure out what the overall sum of those two terms, is it positive or negative for the delta G, the Gibbs free energy. Again, just likewise, when the delta H, the enthalpy, is negative and exothermic, and the entropy term is negative and ordered, I don't know what the sign of delta G is. So therefore, when the sign of delta H, enthalpy, and delta S, entropy, are the same sign, then I cannot figure out what delta G is unless I have numeric values. When the enthalpy and the entropy, that's the delta H and the delta S, are of opposite signs, then I do know what the delta G is. I know whether the reaction is spontaneous or non-spontaneous based on the signs. Okay? So make sure you pay attention to that very carefully. That should give you a real good understanding of what you would expect the numeric values to be when those numeric values do pop up. But if you're not given the numeric values, if they are opposite in sign, then I do know the value of delta G, which is the sum of the two. If they are of the same sign, I do not know what it is. So when it's at equilibrium, then the delta G is going to be a 0. Okay, so 0 for the delta G at equilibrium. That's going to play a role in a future mathematical problem of which we will be solving for. When K, that is the equilibrium constant, K, when it is greater than 1, that means it's product favored. Think about a strong acid. All the strong acids have a Ka value that's greater than 1. That means they dissociate at least 100%. When the K is less than 1, the equilibrium constant is less than 1, that means it's reactant favored. And think about the solubility product constants, the KSP. All those have a K value that's less than 1, they have negative exponents, and they are all reactant favored. So there are many different ways in which we can write this delta G Gibbs free energy and calculating the numeric value of it. It's dependent on the information in which we're given. Okay, and so here's one of them. And delta G is equal to negative RT ln KEQ if we are at equilibrium. Or if we're not at equilibrium, then we're using the Q, which is called the reaction quotient. Remember, back to the equilibrium unit. Might need to review those videos. But the reaction quotient, just like the equilibrium constant, is products over reactants with the stoichiometric coefficients as exponents. Solids and liquids are not included. Okay? So if I know that the reaction is at equilibrium, then delta G is equal to 0. The negative sign is in front of there, and R is the gas constant. We're going to have particular numeric value of the gas constant based on the units in which we will use. T is the temperature, that will be in Kelvin, just like any gas problem. And K is the reaction quotient, K is the equilibrium constant, Q is the reaction quotient, again, depending on where you are at. Products over reactants, stoichiometric coefficients as exponents. Okay, there's another way to write the delta G. It, again, depends on the information in which we are given. So if we are given a table of values of the delta G naught of formation, then we can look those up and just do products minus reactants. Remember the NPR, the N stands for naught. That's at standard conditions, 1 atmosphere pressure and 25 degrees Celsius or 298 Kelvin. Okay, and it would be the products minus the reactants. And then we can also calculate the delta G that way. So there are a variety of different ways of calculating delta G. It's dependent upon the information it's given. However, if we go back to that equation and the spontaneous and non-spontaneous, we can figure out whether that reaction is going to be product favored and spontaneous, or reactant favored and non-spontaneous based on the signs if we are given just the signs. Okay, we've got more, so don't go away. I don't know if you've gotten to this part of math, but if you've gotten to this part of math, you need to be thinking about vectors. And when you sum up vectors, you are adding up those numeric values. Okay, and so if one vector is going in one direction and one vector is going in the opposite direction, then the sum of those two vectors is one of them is negative, one of them is positive, and the larger sign value will take precedence. Okay, so think about vectors and the sum of vectors. We're going to be using that here in this next part. Okay, see, these two boys are pushing this gigantic bale of hay right here. It's a nice round bale of hay. Okay, one boy, it has an enthalpy term that's negative. Okay, and that means that it's an exothermic reaction. When the enthalpy is negative, it's exothermic. The other boy over here has an entropy value that is positive. And that means that this is disordered. So when it is exothermic and disordered, then we know the sign of delta G, and delta G will always be negative and therefore spontaneous and product favored, just like we had in the previous one. But hopefully you understand that the enthalpy as negative and the entropy as positive are both going in the same direction and they're working together. And that's why we know the sign of delta G, and that would be spontaneous and negative for delta G. Hopefully that makes sense. The two terms are working in unison together. Okay, and again, the same equation, delta G naught is equal to delta H minus T delta S. Okay, now we have a number of individuals pushing this Humvee. Okay, so if we have one of these individuals have a positive enthalpy term, okay, we know that that is endothermic if it's positive for the enthalpy. Okay, and another set of these gentlemen are pushing, and it is a negative delta S. When delta S is negative, we know that the system is more ordered than it was before. Now, these two are also working in unison together. They're pushing in the same direction. The vectors are going in the same direction. They're helping each other out. All these men are pushing this Humvee in the same direction, just like the two boys are pushing the hay bale in the same direction. And when it is endothermic and ordered, that means that we know the sign of delta G. It will be positive, and when delta G is positive, we know the reaction is non-spontaneous and reactant-favored. Okay? So this is when the two are of opposite signs. We know the overall sign of Gibbs free energy, and that's delta G. Hopefully you got that. Okay? So when we have this delta G naught is equal to delta H minus T delta S. When it is when it is exothermic, that's negative delta H. And we have a negative delta S, which means it's more ordered. Notice that the signs of the enthalpy, delta H is negative, and the sign of the entropy, more ordered, is negative. They have the same sign. So when they are of the same sign, what is the delta G? Oh, I don't know what the sign is for delta G. When the enthalpy and the entropy are of the same sign, I don't know the sign of delta G unless I have numeric values. Now, likewise, when the delta H, the enthalpy term, is endothermic, and the system is more disordered, that's when the entropy term is positive. They are of the same sign. The enthalpy and the entropy are both positive. They're of the same sign. What is the delta G? Well, I don't know what that is either without plugging numeric values in there. Okay, and let me give you an example of this. So, since both the enthalpy and the entropy are not working in unison, therefore the magnitude, i.e. numeric values, of each must be used in determining the sign of Gibbs free energy and figuring out whether the reaction is either spontaneous or non-spontaneous. Okay, so here's an example here. Okay, we have a car and there's someone driving in the car and they're stepping on the gas. And then we have three individuals pushing the car. Now the person driving the car has it in drive and they're trying to go forward. But the three individuals pushing in the hood of the car, they're trying to make the car essentially go backwards. So they're not working together. They're not working in unison together. They're working in opposite directions. Same with these two gnomes. These two gnomes here are pushing in opposite directions for this round boulder. Okay, so one gnome is pushing on it front ways and going in one direction. The other gnome is pushing on it back ways and going in the opposite direction. So which gnome wins? Well, the strongest one. Which person in the car or the outside wins? Well, the one having more energy pushing. Okay, so I need to take a look at the numeric values when the signs are of the same sign, because they're pushing in opposite directions. Again, this can be of the same sign here as well. When the enthalpy and the entropy are of the same sign, whether they're both negative or both positive, it doesn't matter. I do not know the sign of Gibbs free energy without plugging in numeric values. That's very important. Okay, so we got a little bit more here. I'm going to end this here with a chemistry. So, Florence Flask was dressing for the opera when she turned to her husband and screamed, "Erlenmeyer, my jewels! Someone has stolen my jewels!" Now, my dear," replied her husband, "keep your balance and reflux a moment. Perhaps they're misled." "No, I know they're stolen," cried Florence. "I remember putting them in my burette. We must call a copper." Erlenmeyer did so, and the flatfoot who turned up, one Sherlock Holmes, said the outrage looked like the work of an arch criminal by the name of Laurentium. "We must be careful. He's a free radical, ultraviolet and dangerous. His girlfriend is a chlorine at the palladium. Maybe I can catch him there. With that, he jumped on his carbon cycle in an activated state and sped along the reaction pathway. By Daniel B. Murphy in Precipitations. So I did not, of course, come up with that. I thought that was super cool. If you really read into this, there's a lot of information in this little riddle here about chemistry. You need to get into organic chemistry in order to understand everything. You need to do laboratory chemistry in order to understand everything as well. It's a really super cool riddle. So play that back again and look at it and try to find all the parts that are chemistry related. And then it won't be so much of a mystery to you. Okay, I am the crazy hat chemist, of course, and we got to end with a hat, and I got a great hat here, the great basketball hat. Now, if you like that video, I would greatly appreciate it if you give me a thumbs up. It really, truly helps me out. If you do like all my videos, then please subscribe to my YouTube channel. I would greatly appreciate that as well. If you donate to my website, I'll get you a sticker. If you donate maybe a little bit more, you might even be able to get a cool t-shirt here. Check these cool t-shirts out. Yeah, my son actually made this design right here. So that's why I'm so proud of these t-shirts. I hope you have a fantastic day, and I will see you next time for more cool chemistry videos. Bye for now.